and move to the next talk by Hye-Young Kee from University of Toronto. So Hye-Young.
Okay, so thanks for the organizer for giving me a chance to speak. So I'll be talking about the symmetry analysis and strategies to extract the Kitaev interaction. Seems like this is one of the questions that has been addressed. I don't know how to move this actually. Oh my God. Why this? Okay, so here is okay, good. So I'm going to address the two questions, but given a 10-minute, I don't think I have time to cover both. But in any case, I will quickly talk about the how to generate the Kitaev interaction, and then second question that I want to address is how to estimate the Kitaev strengths out of full Hamiltonian. So examples like this transition metal diaconite or trihalide, you can get some spin 1 or spin 3/2. For the chromium triiodide, for example, we'll have a spin 3/2. But for example, if I have a nickel 2 press, in fact, it's a D8. And way to get the Kitaev interaction is from a spin-orbit coupling in the heavy anion. On the other hand, on the transition metal, one can use the Hund's coupling to generate the larger spin. And the rest, unfortunately, I don't have time to go through microscopics, but you can go over this paper here and take a look at some details. So I'm going to jump into the chromium triiodide here. So as we discussed, this one is having 3 spins of spin 3/2. Just the nearest neighbor models is going to have Heisenberg interaction and Kitaev interaction, gamma interaction. These are all symmetry allowed. In real materials, of course, we have a small trigonal distortion, which is going to squeeze this octahedra and then rotate in a counterclockwise. This one has the R3 bar symmetry, but one can also build up, slightly different structures based on the stacking of the C-axis. Out of this, you can see that already there are 5 terms in the nearest neighbor. Of course, one can add a second nearest neighbors and so on. So I'll discuss that later on. Out of this 5, in fact, this 2 of those, which are the AC, I'm going to refer that as a single ion anisotropy. I think some of you, us using a different notation. I believe Peng Cheng was using a D as the single ion anisotropy there. And gamma prime is another interaction that is induced by the spin-orbit coupling as well as the distortion, meaning the trigonal distortion. And ideal case, we know that Heisenberg, Kitaev, and gamma is allowed, but for a high spin such as spin 3/2 or spin 1, we've shown that gamma is rather very small. Okay, so now let's think about the second question. I want to spend my more or less 9 minutes to discuss about this more recent work than about the Kitaev interaction with the general spin of S. So how do we estimate them? Basically, I'm going to say that we use the symmetry of the full Hamiltonian. So let's look at this little details now. Okay, so let's begin with the generic spin model. This is, again, ideal nearest neighbor octahedra. As I said, we have J Heisenberg, Kitaev, and gamma interaction. And you look at the honeycomb here, and it's 2-dimensional projection of the 3-dimensional object. Even though it's a single layer, we know that this ligand is supposed to be above the these transition metals. And these light gray colors are below the transition metal site. And we normally put the XYZ coordinate, which will be the direction set by the environment, which is the octahedra. So that will be XYZ. And using this coordinate, we'll get the Kitaev and Heisenberg and gamma interactions. On the other hand, one can use the different coordinate, open. One is called the ABC coordinate. C is here out of plane, and A is the direction parallel to the this chain, zigzag chain. And then B axis will be the direction parallel to the one of the bond. Now, looking at this, you can see that there is a mirror plane, which is a C mirror plane, AC mirror plane here. You can see the mapping from this triangle to that triangle. And that's equivalent to the C2B, meaning it's a 180 rotation around the B axis. So that symmetry is preserved. That means that Hamiltonian under this C2B or AC mirror the Hamiltonian has to be invariant. On the other hand, we notice that if I use this as a mirror plane, BC mirror plane, there is no mirror plane here because if I use the plane here, these two are not going to map to the other here. On the other hand, because one of them is above the transition metal and the other is below the transition metal, so that ligand is not going to map to the other. So there is no mirror plane of BC. That is equivalent to say that there is no 180 rotation around the A-axis. That's called C2A. So C2A is broken by the ligand, and that should reflect the broken symmetry should be reflected in the symmetry of the Hamiltonian that we have built based on the microscopics. So I'm going to change the coordinate and then rewrite the Hamiltonian in terms of ABC coordinate. And that is basically doing this linear transformation from the XYZ coordinate to the ABC coordinate. If do so, then we end up with this Hamiltonian. This one is not unfamiliar at all. Some of you probably noticed that this was used in the pyrochloro lattice as well. So these are the AABB are again ABC coordinate, and then that will correspond to XXZ model like, but then there is this bond dependent terms, JAB, JAC. I use a different notation from the literature. So JAB is, some of you who are known, this is going to be J press plus minus minus, and JAC is a JZ press minus, and I just have to change it because it was just too much to write or read. So here phi the gamma is the one that will generate the bond dependence. Depending on the ZXY bond, you have to take a different angles. And of course, these are just the same model, and I just write them in terms of different coordinate. Therefore, JXY, JZ, and JAB, JAC should be related by JK gamma. And that's the relation between them through the linear transformation. Okay, the first thing to note is that JZ minus JXY is just the difference that comes from a gamma interaction. So if you see the in-plane, out-of-plane anisotropy, that will be due to the gamma interaction if you have an ideal honeycomb. Of course, we don't have ideal honeycomb, so the ABC in-plane, out-of-plane anisotropy may come from more than the gamma. For example, single ion anisotropy will be also responsible for the such anisotropy. So as I said, that the C2A is broken, and what the C2A does is that because I'm rotating around the C-axis, SB and SC is going to change the sign, as well as this phi X, phi Y is going to be two different bonds, so they are going to change the sign. So let's see which one of those reflect the broken C2A. So here is again that our Hamiltonian of ideal case, and one should note that I can add now single ion anisotropy DM interaction on the second nearest neighbor with the defect along the C-axis. That's what Peng Cheng has proposed, and I can also add the further nearest neighbor interactions, etc., etc., and then examine. Just inspect the symmetry, which one of those break the C2A. And in fact, that I found that interesting enough that the only term that break the C2A is going to be this JAC. So all of the other terms are just invariant under the C2A except the JAC. In fact, the JAC has to change the sign under the C2A. That's why this Hamiltonian reflects the broken C2A of the underlying lattice. And JAC is a combination of Kitaev and gamma. And then what we propose is basically a magnetic field that can detect broken C2A can be used to isolate this interaction called JAC. So here is the Hamiltonian under the magnetic field. I'm going to apply the magnetic field. The field is in the AC plane. That's just for the other symmetry we don't want to impact. So I'm going to put a magnetic field along the AC plane. Use the two different fields. One is along the above the plane, and the other is below the plane. These two are relayed by C2A. Rotate around the C-axis, A-axis by pi. I'll go from one to the other. So there's two different directional field, and then I'm looking at the spin excitations. And if I have a JAC being 0, because my symmetry, all of this Hamiltonian, is going to be invariant under the rotation around the C2A. The difference between the energy of the basically an eigenvalue of all this full Hamiltonian will be only proportional to the JAC. Okay, so here's a recipe to isolate the Kitaev interaction because JAC is the combination of Kitaev and gamma. So I can first apply the magnetic field in the AC plane with the angle of the theta and measure the spin excitation. Then I rotate, and then B field with the angle of minus theta. Here the theta and minus theta are relayed by C2A symmetry, and then measure the spin excitations. And then difference between the 2 and 4 spin excitation, the energy difference between the two should be proportional to the Kitaev and a gamma. And then in plane, out of plane energy excitations is only difference between the gamma. So if I take the difference between the in plane and out of plane spin difference, spin excitations, this one only for a spin up, I'm going to discuss for the general spin case. Then I'm going to extract the gamma interaction. So if I extract the gamma interaction from this difference, I'll single out the Kitaev interaction. So here is an example. I come up with, I have 5 minutes. Okay, good. Yeah. So here is the examples of, it's angle-dependent ferromagnetic resonance. That's what Ini Lee can do it also, as well as NMR, optical spectroscopy that measures the Q=0 excitations. All of this will apply. First, come up with a magnetic field and rotate from the angle of A-axis to the C-axis. Here, my X-axis is the direction of the field. And the blue is referring to the resonance energy as I change the magnetic field. And from the A to the C-axis, this energy difference will be proportional to the gamma. And then now I come up with a different angle, which is again A-axis to the now below the minus C-axis. And there will be a red. And this red line here will be a resonance energy associated with another field angle. And the difference between the two will appear only if we have finite gamma, finite JAC, which is a K minus gamma. Since I know gamma from here, subtract the gamma from here, then I'll get the Kitaev interaction. Now, then I was talking with experimentalists, and they said, well, having a 2 magnetic field is such a tough job. Can you use the fixed magnetic field direction and measures this interaction? So we said, okay, yes, we can do so. I'm going to fix the magnetic field direction and use instead now 2 different momentum. So for example, neutron scattering will be the best way to measure this. Then we inspect the symmetry of the Hamiltonian again, and we note that when the magnetic field now is in the BC plane, there's one symmetry that is affected by whether we have finite JAC or not. So if the JAC is finite, this time reversal times the C2A is again broken, but if not, then it is preserved. So this difference will be the way to detect the Kitaev interaction. So second recipe is simpler. In fact, I apply the magnetic field in the BC plane with angle of theta. Any angle is fine. And then measure the spin excitations at the M1 and M3 because there is this BC mirror plane that reflected between the two. Difference between the M1 and M3 is going to be proportional to the K minus gamma again. So here is an example. This is for a higher spin S. Gamma is, as I said, it's very small or near the gamma prime, and gamma prime are similar. They cancel out each other. Then JAC is solely the Kitaev interaction. An example like this, I have Heisenberg -1, Kitaev 0.5. You can see that M1 here, M3, these two are related by the C2A. In fact, those two will have a different energy here. And if I reduce the field angle to either in the A plane or C axis, AB plane or C axis, they will be exactly the same. So here again, why the M1 and M3? Because this particular mirror plane is the one that reflected the M1 and M3, and that symmetry is broken again due to the JAC, and that JAC is proportional to the Kitaev interaction. So here is the data for the chromium iodine tree. I have just 2 slides now. So the up triangle and the down triangle here is the data from angle-dependent ferromagnetic resonance from the Ohio group here. And you can see that there's a difference between the angle of the above the plane and below the plane. That's precisely what I was discussed about. In fact, we got this idea from this data. So it was initiated by this experiment. And we are doing a exact diagonalization because Q=0, if you do the mean field theory, all of these features goes away and they just collapse each other. So one has to go beyond the mean field theory to get this. And you can see that data fits quite well. And the data here is using the Kitaev, which is about 1.1. That's roughly about 40% of the Heisenberg. And then we do have finite Zalozinski-Moria interactions along the C-axis. And we also have fit this exactly same value using the Peng-Cheng's neutron scattering. And you can see the nice fitting between the two. So here's my proposal. Applying a field along in the BC plane for a given field, measure the spin excitations, and there will be a difference between the M1 and M3 here. using the same value that we have were able to fit both a ferromagnetic resonance as well as neutron without the field. Now with the field, these two will be different, and that difference is going to be the measure of the Kitaev interaction. So I'm hoping that this proposal will help to search for the candidate materials. With that, thank you for your attention.
Thank you, Hye-young. Let's take questions. This is exactly in the spirit of the targeted questions. There's a dialogue between experiment and theory. I'm sure more questions will emerge as we go on. Let's thank Hye-young and move to the next talk. So
I had a question. I typed on the screen.
In the chat.
oh, sorry, sorry, I didn't see that.
Yeah, I was just curious. What is the size of the magnetic field when you expect this to happen? Do you expect this to happen at the saturation field, or because typically there's a minimum field is required to tune? I mean, are you expecting at each of the field that you apply that the moment to be entirely saturated?
You don't have to, you better, okay, so first of all, we are using a field of, in this case, it's 1 in this ratios around. So for this, for example, here, I'm using exactly the same field that was used in the experiment, as well as the frequency that they have used. You don't want to, if your field is very large, in fact, all of this physics of, so for example, I don't want a magnetic field to be bigger than the Kitaev interaction, then everything will be wiped out by the field. And for the chromium triiodide, you don't need the large field because it's already Heisenberg dominant, because you see that Heisenberg is quite a dominant interaction. Also, some of this I'm just simply following from your estimation for this. So we are just keeping that because that makes the fitting slightly better. But what's most important is basically JK and then this single ion anisotropy with a small DM interactions. So magnetic field will be something like a few Tesla will be just enough, because it's already a ferromagnet.
Thank you.
Yeah.
Okay, thank you. Let's thank Hye-young again.